Hi, welcome to the EEVblog, an electronics engineering video blog of interest to anyone involved in electronics design. I'm your host, Dave Jones. Hi, there's one very misunderstood aspect of electronics, and that's the humble battery, or more precisely, battery capacity. How much energy does one of these things hold? How much current can you get out of it? For how long? How long can you power your device for? How do you do the calculations? Well, it's a very good question, and a lot of people don't know the finer details of it. So I thought we'd have a tutorial on battery capacity. Now, I'm sure everyone's familiar with a standard AA rechargeable battery, and look at the number on it, 2300. And I'm sure you're familiar with that figure, 2300 milliamp hours. 2800 milliamp hours, and you think that's the capacity of the battery measured in milliamp hours. Well, is it? Well, not really. There's a lot more to it. That figure is a very nominal figure. It's borderline bullshit. So what is the capacity of a battery? Well, the battery capacity is the ability of a battery to supply a constant current or a constant amount of energy into a load for a given amount of time. Simple as that. So how do you characterize battery capacity? Well, you can do it in two different ways. There's two ways to specify it. The first, and probably the most common, is, you've probably seen it, amp hours or milliamp hours. It's specified AH or MAAH as the case may be. Now, this isn't strictly the correct way to specify battery capacity because it makes some assumptions. It assumes that it totally ignores the voltage change in the battery, and it assumes that you've got a constant current load, and not all loads are like that, which we'll go into. But basically the capacity, let's say a battery is rated for 1 amp hour here, well, that means it can deliver 1 amp for 1 hour, or it can deliver 0.1 amps for 10 hours, and so forth as you drop in current. Usually that's the upper limit. So 1 amp hour battery, you might be able to draw 2 amp hours from it, but the performance, the capacity, is going to be much less. And the second way to define battery capacity is in what's called watt hours, or WH, and you can get milliwatt hours and stuff like that as well. Same for milliamp hours up here. Now, this is the only true way to measure the actual capacity of the battery, because you're actually measuring the true amount of energy in there, because it takes into account the current and the voltage, watts, V times I, Ohm's law, right? So it doesn't make any assumptions at all. It's the true capacity. And it's the same thing for milliamp hours up here. If it's specified, if you've got a 1 watt hour battery, it means it can deliver 1 watt for 1 hour, or 0.1 watts for 10 hours, and so forth. And once again, you can go higher than that. A 1 watt hour battery, you might be able to draw 2 watts for half an hour, but probably not. It's usually going to be less than that. So measuring in milliamp hours, capacity in milliamp hours, is only valid if you assume that the battery voltage is constant. Now let's take a look at this. It all comes down to what's called the discharge curve, or the discharge characteristic curve of a battery. Now, there's lots of different batteries out there, lots of different technologies, and the curves, the characteristic curves, will all be different shapes, but they will all have a characteristic curve. No battery is perfect. Now, take the case of an ideal battery, okay? What a discharge curve is the battery voltage on the y-axis in volts, in this case 1.5 volts for a AA, a standard single cell alkaline cell everyone's familiar with, versus time on the x-axis. Now, an ideal battery in this case is the one in red. It will start out at 1.5 volts and it will stay at 1.5 volts for all of the time that you are discharging, powering your product. Then all of a sudden it will just die and drop straight off. That's called a brick wall response, an ideal brick wall response, and no battery will even ever come close to giving you that. It'll have a characteristic curve, which is this green line down here, and it'll start out at say 1.5, it'll drop fairly quickly, it might flatten out and go a bit, or just drop at a linear rate for a while, and then curve off right at the end. And that's the true performance. Now, as you'll see with this laptop battery, its capacity is rated in milliamp hours and also in watt hours as well. What does that mean? What's the difference? Well, there's not really much difference in this for this actual application, because what they do to calculate the watt hours is they just take a nominal voltage figure. They don't actually take into account, they just choose a nominal figure in the middle of the curve here somewhere. They don't actually take into account the full change in voltage, usually. Anyway, so there's not much difference, but watt hours is technically a better way to rate battery capacity. It's also the way that they actually rate the different technologies: alkaline, nickel metal hydride, lithium ion, lithium polymer, all that sort of stuff. It's the capacity of those type of batteries and those battery technologies is rated in watt hours per something. So it's watt hours per kilogram of battery material. So just how much energy is in your humble AA or AAA battery? Well, it might surprise you. In fact, it might surprise you a lot. Now, because we're talking watt hour, that's energy. So we can also talk joules as well. It's a direct relationship. Now, 1 joule here equals 1 watt second, not watt hour. So to get your energy in joules, you have to multiply your watt hour figure by 3600, because there's 3600 seconds in an hour. So if you do that and you look at a AAA and a AA battery, your AAA battery, 1.4 watt hours maybe, it varies a lot, as we'll go into, and that's equivalent to about 5,000 odd joules or thereabouts. A AA battery, 2.5 watt hours roughly, or 9,000 joules, okay? Don't even mention your huge D-cell battery or something like that, these tiny little batteries. Now, to give you an idea of what many, many thousands of joules can do, you may have seen this video before. My friend Doug Ford and I blew the shit out of a multimeter with 400 joules. That's right, 400. Even a AAA battery has over 10 times that amount of energy in it. It's incredible. So why can't you blow up a multimeter into flames and make it explode with a AAA battery? Well, it all comes down to the internal resistance. So internal resistance of a battery limits its capability to get the energy out of it and to do some serious damage. Even though there's a massive amount of energy stored in the chemicals in these batteries, a humble AAA or AA battery, a massive amount of energy, you can actually extract it. If you actually extracted the energy out of this and stored it in a massive, big capacitor bank at large voltages with very low ESR, and it's able to dump that energy, then you can well and truly blow a multimeter or something else to dust with a AAA battery. It's amazing. So how do you actually measure the capacity of the battery? Well, if you look at the discharge curve again, that's the green one here, the capacity of any battery is the total area under that curve. And you may know that the area under the curve is an integral. So if you know how to do your integrals and you've got the actual data, you can do an integral of it. But we won't do that. The easier way to actually do it, the more traditional method, is to log the voltage and the current from the battery for a given load. So it must be at a given load, and then you measure the voltage and the current at regular intervals all the way along, and then you can calculate from that the total watt hour capacity of the battery, and that's how it's traditionally done. What actually is the difference between the watt hour capacity and the amp hour capacity? Is there any major practical difference in practice? Well, the answer is not often. That's why a lot of batteries will be specified in amp hour capacity and their discharge will be assumed to be a constant current load. Now, the reason for this is fairly simple. Now, we've already mentioned that the true capacity of a battery is measured in watt hours, and it's the total area under the curve, under the green discharge curve there, which makes sense. But if you want to make the, if you want to measure the, or specify the amp hour capacity of a battery, then you just assume a nominal voltage like that across there. You know, it might be 1.2 volts or something like that. Now, and for a nominal constant current load as well. Now, what happens in that case, when you make those assumptions, you're actually measuring this area in here, which you normally shouldn't be, okay? So there's going to be some extra capacity there, but you're not measuring this one up here. So they can kind of sort of cancel each other out in terms of area. So that's why the constant current amp hour capacity at a certain constant current load might often be similar to the watt hour capacity or the true capacity of the battery. So what sort of things can affect battery capacity? It turns out there's quite a lot of things that can actually affect it. Number one, and we'll go through all these in detail later, but number one, the cutoff voltage that you choose to use in your circuit or the product you've got. Number two, the temperature of the battery, not just the ambient temperature, but we'll go into that. The discharge current or the discharge power or whatever you determine, the discharge rate. The shelf life of the battery will affect it as well. If it's a 2-year-old battery, it will have lost some of its initial capacity. And then you've got the self-discharge as well. Some batteries are a lot better than others, self-discharge, and that's tied into shelf life there as well. So let's look at these. Okay, now let's take a look at some real data sheets. I've got an Energizer AA here. It's an alkaline AA, standard Energizer. You know it, you've used it. And let's take a look at the effect of the cutout voltage on your actual product. So if you're actually designing a product, and let's actually take a look at the discharge, a typical discharge curve right here. Now, if you're actually designing a product, here is the voltage of the battery. Now, if you design your product to cut out at, say, or give you a low battery warning error at, say, 1.1 volts here, then bingo, look at all this capacity under the curve here that you're throwing away. You're just pissing away all of that battery capacity. Now, it gets even worse if you do 1.2. Look at 1.2 volts. If you set it to cut out at that, you're wasting half of your battery capacity. It's crazy. So a well-designed product will have as low a cutout voltage as possible. And for an alkaline, that's about 0.8 volts. A superbly designed product will operate all the way down to 0.8 volts per cell. So when you're actually designing your circuit to work off AA or AAA alkaline cells or primary cells, these are the voltages that you should design your product to work down to. Ideally, if you want to use the most capacity inside this battery that you can, then this is what you should do. For a single cell, 0.8 volts, as I said, because that just drops off like a brick wall down at 0.8 volts there. So, but a 2-cell design, nominally 3 volts, 1.6 volts is what you want it to work down to. 3-cell and 4-cell, a nominal 6-volt system, 3.2 volts down to. And a 6-cell system or your standard 9-volt battery like this, ideally your product should work down to 4.8 volts. And this is why in my product reviews you will see that I actually measure the cutout voltage of the battery. So if a multimeter is working from this 9-volt battery and its cutout voltage is, you know, 6.5 or 7 volts, as some of them are, or even higher, then they're just pissing away a ton of capacity in the battery. It's crazy. Don't do it. Now, one of the big things that affects batteries, particularly alkaline cells, is the temperature. Not just the ambient temperature, but the temperature of the cell as well, and in particular, low temperatures. Now, this is the Energizer L91. It's a AA, but it's one of these lithium. It's a lithium ion disulfide battery, and you've probably seen and you've probably heard how great they are and how they work at low temperatures and how they work at higher discharge currents and all that. But they've actually got they've got some charts down here for the temperature, and let's take a look at them where they compare this lithium to a standard alkaline cell. Now, these dark bars here represent the lithium battery, and these ones and the other one there represents the alkaline. And as you can see, this is at cold temperature here, 0 degrees C, and this is at room temperature, 21 degrees C over here. Now, as you can see, at room temperature, at different discharge currents, you can see how the lithium totally outperforms the alkaline cell. But the interesting thing to note is that notice the level of the alkaline cells here, 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 and here. Now that's at room temperature, 21 degrees. Once you take them down to 0 degrees, look, they're really dropped. They've more than halved. So you're losing a lot of your capacity, especially at the high discharge temperatures. Now, that's pretty obvious when you take a look at the reason for it. It's pretty obvious. If you take a look at a temperature curve here, basically the series resistance in the cell versus temperature on the x-axis here, this is positive temperature, this is 40 degrees up here, and minus 40 degrees down here. You'll see that as the temperature decreases, the series resistance in the cell increases. So you're going to lose capacity due to your IR increasing. And of course, the discharge current affects the capacity greatly as well. Now, as you can see, we've got the capacity of the battery in milliamp hours up here from 0 to 3000, and different discharge currents, 25 milliamps up to 500 milliamps. As you can see, at 25 milliamps, quite a low discharge current for a AA battery. Its capacity is a nominal, say, 2800 milliamp hours, and that's the figure that you'll typically hear about. But hey, if you go to 500 milliamps, then the capacity is, look, it's only about 1200 milliamp hours, a big difference. And if you take a look at shelf life here, then you can see that after 7 years from the date of manufacture at 21 degrees C, it's only going to have 80% of its initial capacity. Now, those figures aren't often true. It depends on the actual manufacturing quality of this particular batch of it. You can't always rely on that figure strictly, so take it with a grain of salt. Now comes the big reason why batteries have the discharge characteristic curve that they do, and why it's not ideal like that. It's because of the internal resistance of the battery. Now, the internal resistance, or the IR, or sometimes called the ESR of the battery, the equivalent series resistance, is actually made up of two different types of resistances in series. One is the electrical resistance, and that's like the internal metal contacts and things like that, internal to the construction of the battery. And the other part is the what's called the ionic resistance, or the electrochemical reaction inside the battery. And that's to do with the electrolyte, the conductivity of the electrolyte, the surface area of the electrode, and polarization and that sort of stuff. And this one acts much slower than the electrical resistance. The electrical resistance will actually will always be there, bang, straight on, but the ionic resistance has a bit of lag, so it will only show up under pulse conditions. Now, as you can see, this is the data sheet for a CR2032 coin cell battery, which you're all familiar with, and it just happens to have a pulse characteristic graph like this, which actually is the method used to measure these two different types of resistances down here. And you can actually see when you apply a pulse like this is the battery voltage in volts up here, and this is time over here. And as you can see, if you apply a pulse, bang here, then it drops down suddenly. And that part there, the very steep part, is the electrical resistance down here, which works straight away. Okay, it's always there. And then the ionic, then after some time, the ionic resistance will kick in and go like that. It'll take some time, but it'll eventually settle down to a fixed value. And the total IR that you see in the graphs here, here's a graph of the IR versus the characteristic discharge curve. you'll see that the IR is just one particular value, which they'll actually specify up here in the data sheet. There it is. Typical IR will start out at 10 ohms and increase to 40 ohms at the end of its life. Now, what I love about this particular discharge characteristic graph is it shows beautifully, it's splendid, how the IR increases at the same rate as the characteristic discharge curve decreases. Now, I've actually made a transparency of this, look, okay? Now, it's no coincidence that if we flip that over, look what happens. It matches the discharge characteristic curve almost exactly. Magic, huh? And of course, when you're talking about battery capacity, the load type is all important. Now, there are 3 different types of loads, and you might see these 3 types. In fact, you might see all 3 types on a particular data sheet for a battery. Now, the most common is the constant current load type. Now, the second type is the constant resistance type, and as it says, it's a resistance. So to test that, they literally put, you know, a 10 ohm or a 100 ohm resistor across the battery, and that's it. Well, most circuits aren't going to be constant resistance, are they? Really? You know, they're going to actually be constant current, or the third type, which is constant power. Now, this is probably the most accurate one for most circuits you're going to actually design, most products, which is why the watt-hour capacity, because watt-hours is power, okay? Watts is power. So the constant power graph might be more important for you if you've got a DC to DC converter circuit driving your particular circuit. Then you probably might want to look at the constant power graph instead of the constant current or constant resistance characteristic graphs. And in a previous blog, I've showed how you can design a simple dummy load that can actually do all 3 of these in one. It's just got an op-amp, a FET, and a load resistor down here. And by hooking in my example in the previous blog, I just hooked this up to a voltage source, a pot, and that just worked as a constant current load. But if you feed this back, if you feed the voltage back to a microcontroller and you actually control the input, if you feed via a DAC, so if you use an intelligent micro in there, you can actually, by doing some simple Ohm's law calculations on the fly and actually changing this as the thing discharges, you can generate a constant resistance or a constant power in this load. So this is a pretty handy way to measure battery capacity. And there's actually a 4th type of load as well, and that is the pulse load. And the pulse load can actually apply to any 3 of these types. And it just means that they'll typically have, if this is, say, current up here, then they might actually pulse it like this. They might have a steady low current down here and pulse it to a high current periodically. And as you can see, a good data sheet will actually have constant power performance curves, and will also have constant current performance curves. And down here it's got these what they call industry standard tests, and they're based on old, you know, transistor radio kind of things, and they're actually constant resistance tests, in this case 43 ohms for 4 hours per day and stuff like that. They give service hours. So you need to pick the performance graph that you think is acceptable for the particular type of load that your product is going to represent. So how do you calculate the battery life of your particular product? Well, as I said, you've got to pick the type of load which is typical of your product. Constant current, constant power, constant resistance, whatever, maybe a combination, maybe it's got some pulse stuff as well. But generally speaking, it's actually pretty darn hard to get a really accurate estimate of the battery life for your product based on just the characteristic curves in the data sheet. Really, if you're serious about it, there is no substitute for actually measuring the actual battery life in your actual product. And often that is just what you have to do. You simply don't have enough data available to actually make a true calculation. So you've just got to suck it and see. I mean, sometimes you can just, rules of thumb, ballpark stuff. If a battery's 2000 milliamp hours, and you know it's going to roughly draw 50 milliamps plus minus 25, something like that. You can assume it's constant current, and you can just, well, do the simple figures and calculate it's going to have X amount of life. And typically those ballpark figures are usually pretty good. You might drop it down by 30% or calculate it and then drop it back by 30%, but really it's just a guess. Now of course sometimes it's okay to just go near enough, and well, my circuit's got a DC to DC converter and it's delivering a constant power into my product, and because the efficiency curve doesn't drop off too much, you can say that there's a constant input power from the battery as well, and well, everything's hunky-dory, and you can get some reasonably accurate ballpark measurements from that. So it's not bad engineering at all to just wet the finger and go near enough, in the ballpark. Especially for first order calculations, just for product viability and general comparison work. Estimations are great. So there you have it. Let's go through a quick summary or a cheat sheet of what battery capacity is all about. Now, number one, it's all about the battery cutoff voltage. There's absolutely no point specifying the capacity of a battery if you don't know what the cutoff, if you don't specify or know what the cutoff voltage is. It's crazy. Second, if you increase the current or increase the load current, then you decrease the overall capacity of the battery due to IR. If you decrease the temperature, you decrease the capacity. And remember, that's the temperature of the cell, not necessarily the ambient temperature, because the cell can heat up due to IR down here. Now, you've got to know your load type. Constant current, constant power, constant resistance. Choose the one that's most appropriate for your particular product when you're dealing with the graphs. And if you're serious, use watt hour plus constant power, because true watt hour, that is the true capacity of the battery. Milliamp hours is a bit of a guesstimate, okay? And really the only way to measure true capacity and battery life in your particular product is to actually measure it in your circuit. Do some real world tests. And IR is everything. It's all about the internal resistance of the battery. And that means power wasted in your product, just pissed away because you've got this excess current. If you try and draw too much current from a AA battery, if you try and draw 2 amps out of this thing, or 4 amps or 5 amps, it's just not going to do it because of the internal resistance. It's going to heat up, it's going to have a short life, and your characteristic curves aren't worth squat. Now, no talk about battery capacity would be complete without mentioning a rather obscure law, which not very often used. A lot of people wouldn't have even heard of it, but you may come across it. It's worth mentioning briefly, Peugeot's law, and it basically is the reduction in capacity at higher currents, as we've seen and discussed in the characteristic curves and all the rest of it. Okay, and it's actually a more complex formula than this. This is a simplified version, but this is most commonly used. Basically, T equals C on I to the power of K, where K is Peugeot's constant, which is actually an empirical measured value for the battery. 1.0 being ideal, 1.2 might be typical, something like that for a battery. T is the discharge time, theoretical capacity, and the discharge current. So as you can see, the discharge time goes down if K actually goes up, the constant. So your nominal 1 amp hour battery might drop to 0.8 amp hours or something like that. Look it up if you want to know more.